Today we will talk about some examples and applications of the universal property of free groups. Okay, so we'll do 4 examples today. So let me skip to the very first one. So here's the example or a problem. Let S be a set, and if we take 2 elements A and B in the set which are not equal to each other, then the problem is the following: prove that the equivalence class of A and the equivalence class of B are not equal in the free group f of S. Okay, A and B are unequal elements of the set S. The question is to prove that when we take the corresponding equivalence classes of just the singleton word A and the singleton word B, those 2 equivalence classes cannot somehow become equal in f of S. Another way of saying this is that the map J from the set S to Fs that we talked about in the universal property, that map is in fact injective. So this is the map X going to the equivalence class of X. Okay, so at this point, those of you who are sort of watching the video, I would encourage you very much to try and try your hand at this problem first, but maybe pause the video and try it. But let me go on. Now, for those who want a little bit more of a hint to try this problem, here's the very first thing. So observe, what is it that we really want to prove? So we are trying to prove the following, that if I have 2 elements, so let's proceed by contradiction here. So suppose one thing we could try is to try an argument by contradiction. So suppose these 2 equivalence classes are actually equal to each other in the free group. What does that mean? It means that if I take A and I multiply it by B inverse, I should get the identity in the free group. Okay, now what does that mean? Well, if you recall what the inverse of B was, this is just B prime. So this is the identity, and now this concatenation, the product of A with B prime is just the concatenation, which is the word AB prime is the identity. So the final thing that you really need to do is to derive a contradiction from this fact. So what do we finally conclude? That AB prime is equivalent under that rewriting rules equivalence relation to the empty word. Okay, so this is what it means for the equivalence class A and B to be equal to each other. Okay, so at this point, again, those who would like to use this hint to try this problem, I would encourage you to pause the video and sort of try your hand at it. Okay, so let me move on. So here's sort of the final solution to this problem. So recall from the hint that this is sort of what we assumed, that we proceeded by contradiction. If we assume that A equals B, then we concluded that AB prime, this word, is equivalent to the empty word. Okay, so this is of course thought of as words in the augmented alphabet S hat. Now why is this a contradiction? Where is the contradiction going to come from? So observe, what does this equivalence mean? So let me start with the empty word. So I'm saying the empty word is equivalent to the word AB prime, which means that from the empty word I can find a sequence of rewriting steps, basic rewriting steps, or a chain which will finally get me to the word AB prime. Okay, so each of these arrows is a basic rewriting rule. Now I claim the following, that when you apply a basic rewriting rule to the empty word, what you get at every step, so each of these words here, each of the words in the chain has the following property, that it has an equal number of A's and A primes. Okay, likewise B's and B primes, but let's focus on one of the alphabets. So I claim that every W that is equivalent to the empty word has an equal number of A's and A primes. Okay, a and a dash, there should be the same number of these two in the word W. Okay, and the proof is, well, more or less clear. We just have to look at what a basic rewriting rule does. It either inserts, so this just follows from what the basic rewriting rules were. It either takes a dash. If you have an occurrence of a dash, you can replace it by the empty word. So or conversely, if you have the empty subword, you can replace it by a dash. Now observe that these two processes, what happens here is, if I have a word, so for example, if a word has an equal number of a's and a dashes, and I take a subword, so here's a word, and let's assume this word has an equal number of a's and a dashes, and what this first basic rewriting rule says is, I take, say, suppose there is an a and an a dash which occur consecutively, then this rule says I am allowed to delete that from my word to obtain my new word, right? Now if my original word had, say, 10 a's and 10 a dashes, then the new word will have 9 a's and 9 a dashes, so it will continue to have an equal number of a and a dashes. Okay, now the other rewriting rule is even simpler. It says I can either replace bb dash by the empty word or the empty word by bb dash. Here, since I'm only focusing on the alphabet A, if my word has some number of a's and a dashes, and suppose I apply this rewriting rule, then the number of a's and a dashes in the new word does not change, because all I'm doing here is taking a bb dash and making it empty, or taking the empty word and making it bb dash. Okay, so I would encourage you to play with some examples to get an actual idea of what we are doing. So the key point here is that if you take the empty word, and no matter which one of the basic rewriting rules you apply, and you keep applying it successively, at every step the number of every word you get has the following important property, that the number of a's and the number of a dashes in that word are equal to each other. Okay, now that automatically implies that in this chain you cannot finally end up with this word ab prime. Okay, why? Because this final word that we have, it has one occurrence of a and 0 occurrences of a dash, right? So this word has an unequal number of a's and a dashes, so this word couldn't possibly have arisen from a sequence of basic rewriting rules applied to the empty word. Okay, so that's the first example. So this was a simple enough thing. We were just trying to understand what basic rewriting rules do to the number of a's and a dashes, and in fact this is related to the example in one of our earlier videos in which we said the free group on a single alphabet, single letter, is isomorphic to the group of integers. And if you remember, the homomorphism there was just given a word, you associate to it the number of a's minus the number of a dashes. Okay, this is more or less the same idea. Okay, so let's move on to the second example. So here's the question. It says, if I have two elements of S, then prove that which are unequal, then prove that in the free group the product AB is not the same as the product BA. Okay, so I hope the question is clear. If you take two elements of S which are not equal, then the corresponding elements in the free group, the equivalence classes of A and B, do not commute with each other. And again, this is a good place to stop the video and sort of try your hand at this problem. So I would very much encourage you to do that. Okay, now here's a hint. So let's sort of proceed the way we did earlier, which is to try and see what we can get by a contradiction argument. Suppose we proceed by contradiction. So let's do contradiction. So suppose we assume that AB is the same as BA. Okay, then by the same reasoning as before, the left hand side is AB, the equivalence class of the word AB. The right hand side is the equivalence class of the word BA. And if those two equivalence classes are the same, it means AB and BA are equal to each other, or are equivalent to each other. In fact, we can sort of do the same thing that we did before. So instead of writing it in this way, let me do what I did to the earlier problem, which is if AB equals BA, let me do it to the next step. I can replace the right hand side. I put them both onto the left hand side as inverses. So this means A inverse B inverse is the identity. Okay, and now again as before, A inverse and B inverse are just the equivalence classes of the words A prime and B prime. So this means that this is the identity, and that in turn implies that AB A prime B prime is equivalent to the empty word. Okay, so we are sort of in a similar situation as in example 1. We have a word which is equivalent to the empty word. Okay, but observe, unlike the earlier example, we don't get an automatic contradiction, because this word here AB A prime B prime has an equal number of A's and A primes. It has one A and one A prime. It has one B and one B prime. Okay, so at least it satisfies that primary requirement for a word to be equivalent to the empty word. It's a necessary condition, but we still somehow need to get a contradiction out of this. Okay, so it will turn out we have to prove that this can't be the case, that AB A prime B prime can't be equivalent to the empty word. Okay, and since what I'm trying to do here is to give you a hint to do this problem, use instead, so here's the way to proceed. We'll use the universal property. Okay, so try to come up with a way of using the universal property of free groups to prove that AB A prime B prime can't be equivalent to the empty word, or equivalently that AB cannot be the same as B. I mean, whatever we need to prove. Okay, so let me move on to the solution next. Again, I would encourage everyone to pause here and try your hand at it. Okay, so here's the proof, which uses a very nice application of the universal property. So what we do is the following. So recall, what does the universal property look like? It says the following: take any group K. So what all do you have to choose? You must choose a group K, and you must choose a map. This is another choice here. You must choose a function, any set map from the set S to K. Okay, so you choose these two things, K and F, and having done that, what the universal property says is, I have a map from the free group to K. It's a group homomorphism. So main properties, it's a group homomorphism. Okay, and further, F tilde it's related to F in the following way: F tilde of J of X is just F of X. In other words, the diagram commutes, right? So this diagram commutes. That was what the universal property said. And there is a uniqueness as well, which we won't really need in this example. Okay, so if you choose K and F cleverly enough, you should be able to prove what we need to prove in this case, that these two are not the same. Okay, so let's do that. Let's make the following choices. So for K, I will choose K to be any non-abelian group. Okay, so let's pick a non-abelian group, and well, what's one of the easiest examples? Well, you can pick K to be, say, the symmetric group S3. Okay, so for concreteness, let's pick an actual group. I take K to be S3, the symmetric group. Okay, now I need to define my map F. So to define my map F, let me pick the following. I will pick two auxiliary elements. So I have a non-abelian group K. Now let me pick two elements A and B from this group K. Let A, B belong to this group K. Be non-commuting, be such that A, B is not equal to B. So I have picked a group S3, and now I have to pick two non-commuting elements from this group. So let me pick them as follows. So I take A to be the 2 cycle, which means it is, so it written in cycle notation, it is 1, 2. And if you recall our notation in terms of permutations, it's 1, 2, 3, 1, 2, 3. So 1, it's a bijection of the set 1, 2, 3. 1 goes to 2, 2 goes to 1, and 3 goes to 3. So this is the permutation A. The permutation B is a similar thing. It's 2, 3. So again, in terms of our diagram, it's 2 and 3 are exchanged and 1 goes to 1. Okay, so 1, 2, 3, 1, 2, 3. Okay, so that's the definition of A and B. Now, having chosen these two non-commuting elements, let's define this function f next. So what is f? F is as follows: from the set S to K. So S has these two distinguished elements A and B. So let me map A to capital A, this element here, B to capital B. Okay, and of course there are lots of other elements potentially in S, and I don't really care what I do to them. So I can send them to any element, to different elements even of K. So I can send each of them to any element of K. Okay, so if you want something concrete, example, I can send all of them to the identity of K if you wish. Okay, so this choice really doesn't matter. You can do what you want. Okay, so I hope this is clear so far. I've picked the group of, in general, I can pick any non-abelian group. I can pick any two non-commuting elements A and B in that non-abelian group. And I'll define my function f to be the one which sends small a to capital A, small b to capital B, and it does whatever it wants to the remaining elements of my set. Okay, so having done this, let's see, where does that put us? The universal property now says, by the universal property of free groups, we conclude that there is a map f tilde, a group homomorphism from the free group to the group K, satisfying the following property, that f tilde maps the equivalence class of X to whatever f does to X. Okay. Now, in particular, so this is the important property here, it's a group homomorphism. Now, in particular, let me see what. So, I'll take X to be A and B, those two specific elements. So, f tilde of A gives me f of A. So, that's my element capital A in K. F tilde of B is my element f of B, which is B. Now, let's apply, let's get our contradiction. Let's go back to the original question. Now, suppose it were true that AB is the same as BA. We'll see how our map f tilde is going to help us. Let's do the following. Let's apply f tilde to both sides. Okay, so these two elements here, I mean these two sides of the equality, they are both elements of the free group. I apply the homomorphism f tilde to each of them. So f tilde will take the left hand side to an element of K and the right hand side to an element of K. So let's see what is f tilde of the left hand side. So okay, so I'm going to apply f tilde to both sides, and this is what I get. Now comes the important thing. Remember, f tilde is a homomorphism. Okay, and this is now a product of elements. So this is going to be f tilde of A times f tilde of B, and that of course by choice is AB. If you do it to the other side, it's going to give you f tilde of B times f tilde of A. That is the element BA. Okay, so what do we conclude? If this equality holds, then it must also be true that AB is the same as BA. Okay, but that is a contradiction because we specifically chose two elements A and B which are non-commuting. Okay, so in some sense so that completes this proof here. In some sense, the broad idea of these sorts of proofs is the following: any property that you want to show holds in the free group, for example that A and B don't commute, you try and produce a concrete group in which you and certain elements in that concrete group which don't have that property. Okay, so I have to show, if I have to show, for example, the AB is not equal to BA, one way of doing it is this, find a group in which there are two elements A and B where AB is not equal to BA, and then you just map these elements small a and small b to capital A and capital B. Okay, so we'll see another example of this kind, and hopefully things will become clearer. So moving on to example 3, it's the following. If I have a set S and I take an element A in the set S, prove that the nth power of that equivalence class is not the identity. Okay, so this is we claim that this is not the identity in the free group for any value of n greater than or equal to 1. In other words, the element A is not of finite order. Claim is it has infinite order. Okay, and again pause the video, think about it, and in this case the hint is, well, the same thing, use the universal property. Okay, and sort of study how example 2 worked. Okay, and see if you can prove this in a similar way. Okay, moving on. So here's the proof. Again, similarly, I just need to pick a group K. So I choose K to be an infinite group. Which has an element of infinite order. Okay, which has an element of infinite order. I mean, it can be this general if you want, but let's be very concrete here. Suppose I take K to be, so let me choose K to be the group of integers under addition, and let me take an element of infinite order in this group. So I will take A to be the number 1. Okay, so observe that this number A has infinite order. Because you know what is A power n in this group? Well, A power n is just a plus n times, because the operation is just addition, and that by definition it's 1 plus 1 plus 1 n times, which is the number n. Okay, and the number n can never equal 0, which is the additive identity in the group set, right? So the element 1 in Z has infinite order. Okay, so we have found a group with an element of infinite order, and now let's just use the universal property as follows. So I take my set S, and to the group K I define my function f as follows. This special element A that I am looking at, I will map it to this element of infinite order, and all the other elements I don't really care. I can map it to any elements of, different elements of Z, different x's can map to different elements, for example. Okay, so I don't care about the rest. So I define a function f from S to Z, and by the universal property, what does that give me? It gives me there exists a group homomorphism f tilde from the free group to Z, such that f tilde of x is f of x for all x in S, and as you can imagine, in particular all we are going to do is just take this particular value of x, which is A. So in particular, if I look at f tilde on A, this is going to give me capital A. Okay, and now we'll derive the contradiction in much the same way that we did earlier, as follows. So now for the contradiction. Now suppose A power n is the identity in the free group, and let's do the following. We'll apply f tilde to both sides. Okay, now f tilde on the left hand side, again we have to use the fact that f tilde is a homomorphism. So f tilde of A power n equals f tilde of the identity. Now on the left hand side, f tilde of A power n, because it is a homomorphism, is the same as f tilde of A, the whole thing power n, which in turn is just A power n. Okay, where this is of course the operation in the, so this is 0 in Z. So this is the operation in if you wish, the operation in the integers. So this is actually okay. So let's do it this way: a power n, which means a plus n times, which because a is 1, this is just the number n. Okay, and now here's your contradiction. So what we are really using here is that the element a has infinite order, it cannot have finite order. So the contradiction now is this. So we have shown that n equals 0. Okay, and that's a contradiction. Okay, so we have proceeded by contradiction. We have assumed that the element a has finite order and concluded that this element capital A would have to have finite order. Okay, and that's a contradiction. Okay, so now for the last example, which is show that there exists a surjective homomorphism, group homomorphism from the free group to the group S3 of permutations of 1, 2 and 3. Okay, so again think about it, pause the video here. Now here's a hint, how do you construct homomorphisms from free groups? So hint, how does one construct homomorphisms from free groups to other groups? Well, all you have to do is to just construct just a set map, construct an appropriate function from just the set AB to the group S3. It is just it has no additional property, it's just a function. If you construct an appropriate function, then use the universal property. Use the universal property to obtain a group homomorphism from the free group. Okay, so in some sense, a group homomorphism from the free group to another group, this information is really in some sense the same information as just a map of sets from the set AB to S3. Okay, so if you are asked to construct this guy, then it's sort of enough to construct the guy on top. Okay, of course you should do it in such a way that the resulting homomorphism has the properties you want. Okay, so focus on this, try to find an appropriate function from the set AB to S3. Okay, so again pause and think about it using this hint. Now here's the solution proof. So let's do the following. So let's construct a function from AB to S3 first, from the set AB, which is the set S, to S3. Let me say A and B. So let's do the following. Let me map A to the cycle 1, 2 and B to the cycle 2, 3. Okay, these were the very same two things that we called capital A and capital B in example 2. Okay, so let me map A and B to these two guys, and let me look at let's call this F, and let's use the universal property. This therefore induces a group homomorphism from here to S3, which is called F tilde. Okay, so there exists a group homomorphism from the free group to S3. Call this F tilde, and what does this guy do? It sends A to this cycle A, B to this cycle B. Okay, so I know the existence of this by means of the universal property. Now here's the important thing. Our claim is that this is the map we want. Claim F tilde is surjective. So recall, surjective just means onto. So we claim F tilde is an onto function. Okay, why should F tilde be onto? Well, here's what we know. What does it mean to say that F tilde is onto? It means that the range of F tilde is the entire group S3. Okay, but observe, here's what we know about the range at least. So observe that because F tilde is a homomorphism, the range of F tilde, the range of a homomorphism is always a subgroup. the subgroup of the group on the right, the codomain. Okay, so if I have a homomorphism, because F tilde is a homomorphism, okay, so a simple exercise if you haven't seen this before. Now what more do we know? We know that this element capital A and capital B both belong to the range. Okay, so the range is a subgroup of S3, it contains capital A and capital B. Well, then all you have to check is that you can, it has to contain all the other elements of S3 as well. In other words, I can get every other element of S3 by sort of taking products, for example, of elements A and B. Okay, so well, let me leave that little bit as an exercise. So exercise, check that, well, another way of saying it is that the subgroup generated by capital A and capital B in S3, the subgroup of S3 generated by these two elements is actually the entire group S3. Okay, and how do we check this? Well, you sort of have to keep taking various products and so on to see that you get every element. So here's one example. If I take AB, which is the cycle 1 2 times the cycle 2 3, then you just have to check using the diagrams, for example. What this does is, so it's a composition of these two maps. So 2 goes to 3 under the second map, 3 goes to itself, so this is 2 goes to 3. So I claim this is just a 3 cycle 1 2 3. In other words, this is the map which sends 1 goes to 2, 2 goes to 3, and 3 goes to 1. So it's this cycle. Okay, similarly, if you sort of look at BA, then you will get 1 3 2, and you sort of have to see what you will do to get the other element. So here's the little exercise. What products of A's and B's will give you the element 1 3 of S3? Okay, so the identity, similarly, how will you get the identity if you wish? Try write in terms of A. Well, identity is easy, I suppose. You can just say identity is A square. In other words, I just take A with itself, what I get is the identity. Okay, so this just is another way of saying that every element of S3 is in the subgroup generated by these two elements, capital A and capital B. So of course this means that the range has to be the entire group S3. Okay, so that completes the proof. So we have used the universal property to construct a map, and then we have shown that this map has full range. Okay, now here's sort of some additional questions for you to think about. Is there any other such function? Are there other such functions? Are there other surjective homomorphisms? From the free group on two generators to S3. So we constructed one, but are there other ways of constructing them? And maybe sort of related, but maybe slightly harder question. How many such homomorphisms are there? How many such surjective homomorphisms are there? Okay, it's a finite number. Okay, there are only finitely many of them. Your task is to try and find out exactly how many there are. Okay, so we'll stop here.